Let's have a little class excitement today. Let's hear it. You, that was good, Sarah. Woo, chemistry. All right, no rapping. Christmas rapping, maybe. So, kinetics. You've just seen now 4 different demonstrations that show you how we can increase reaction rates by changing things that affect how reactions collide and the energy with which they collide. So, what we're going to look at in this unit are specifically 3 different ways to find what we call a rate law. In order to get to the whole concept of rate laws, though, I do need to do some introductions with you guys. Here is what we study in kinetics. We've already talked about these factors. You saw demonstrations on them all. One we didn't actually see a demo for was pressure. Okay, how does increasing pressure increase the rate of a reaction? Molecules have to be closer together. So right off the cuff, you should know this only occurs in what state of matter? Gases. If we change pressure with solids and liquid reactions, nothing's going to happen. But if gases molecules are closer together, they're going to have a chance of colliding more often and with more energy. So that's going to be our fifth thing that affects reaction rates. So next, what I want to look at is, what is rate? If I told you to go drive your car, what do you measure your rate of your car driving in? Miles per hour, which is a change in what over what? Distance over time. In rates of reactions, we don't look at distance. Instead, we look at change of concentration over time. We can look at it 2 ways. We can look at the change of product produced, or we can just look at how much of the reactant disappears. We can look at it in respect from the reactant. You can't have a negative rate, so can anyone explain to me why we have a negative there? Because the reactant amount is dissipating. So our reactant final minus initial would end up being a negative change in concentration. Well, we can't have a negative rate, so that's why there's just a little negative in front. Loss of reactants is actually the more popular way that we are going to study when we're determining rate laws of reactions. Okay, so let's look at this. Up until this point, you guys have studied and have learned that these coefficients are ratios of what? Moles. What else could that be a ratio of? Molecules. If you're at STP, what else could that be a ratio of? Liters. Okay. But one thing you might have never considered was that this is also a ratio of rates. So it is fair to say that since there's a 2 in front of N2O5, it is going to disappear half the rate that NO2 appears. NO2 is going to appear twice as fast as N2O5 disappears. It's a 2 to 4 to 1 ratio. O2 is going to appear half as fast as N2O5 disappears. Okay, so you can look at all these as ratios of rates. So looking at this, we're going to do what we call relative rates. I'm just arbitrarily going to set everything equal to the rate of N2O5. Okay? Looking at this, we know that NO2, based on the coefficients, is twice as fast in appearing as N2O5 disappears. So how do I make the rates the same? This is twice as fast, so what do I need to do to make it the same as that? Half it. That's why there's a half there. Okay? O2 is half as fast as N2O5. It's a slow booger, so what do we want to do to make it the same as N2O5? Double it. Again, I arbitrarily picked N2O5. Let's go ahead and make things equal to NO2. Change in NO2 concentration over time. Okay? What would I do to N2O5? NO2 is the fastest one there. I would double, good, the concentration of N2O5, and I would quadruple the concentration, the change in concentration of O2 over time. Okay? Yeah, we do need a negative there. But I'm not going to get hung up there. They're going to give you numbers, and you're always going to know it needs to be positive, and it'll make sense. Okay, skip this next slide and go over to the problem number 1. Number 1 is you're given the rates, and you're told to find the actual coefficients. So this is really, really easy because you're just going to relate. Let's relate A to B. What happened to the rate compared from A to B? What? Triple times 3. So what am I going to do to this coefficient? Times 3, and what do I get? 6. Ooh, that's so hard. Okay. What do you want to compare C to? I like clean numbers. Yeah, B to there, what did I do? Divide by 2. So in front of B, I had, oh wait, y'all didn't stop me from doing something stupid. What did I just do? I said, ooh, it's so easy. And Milo's cracking up like it's the funniest thing on the planet. We multiply by 3. What do we multiply by 3? 2. Would y'all please stop me from doing stuff like that, especially on tape? Good God. So then, thanks, Milo. Thanks for that, Mr. Superior. All right, so right here, we're going to take B's coefficient and divide it by 2, and what do we get here? 3. You're on my list, Milo. Yeah, I'm sure now. All right, and then how are we going to find the coefficient in front of D? No, I'm going to go from here to there to make life easier. I'm going to divide it by 2. I'm going to divide the A by 2, so I get 1. Okay? It was. I thought it was easy. Apparently, math is hard. So the big important thing about this unit is being able to find rate laws. There are 3 ways to find rate laws, and to the left of this board, I have them written down, and we're going to check them off as we finish it. But the first way to find a rate law is the use of a mechanism, and we'll learn the other 2 later. But you're asking, what is a rate law? Well, I don't have a reaction here. It says the data for the above reaction. Well, where the heck's my reaction? I don't know where it went. So I'm going to write another reaction. A plus B gives us C plus D. That's an overall reaction. To write a rate law to that reaction, I need some information. What a rate law tells me is the rate of a reaction under different conditions. To write a rate law, it's always rate is equal to K times the concentration of my reactants raised to some coefficients. I don't know anything about those coefficients unless I have some experimental data or unless I have a mechanism. Those coefficients up top are called the order of the reaction. That K is called the rate constant. Once those are determined and I actually have numbers in those spots, that's a set rate law. Then I can vary concentrations and see what happens to my rates. So in industry, if I have a particular reaction and I want to know, oh, which one, A or B, should I increase to make more product? Well, you're going to pick one with a higher order and things like that. So once rate laws set, they become really, really useful. So how do we find a rate law? Let's do it. Skip on. This page right here, read after the lesson because it'll make sense. Okay, it'll be a good little review. In order to find a rate law, the first way, we need a mechanism. Up until this point in your career, we've kind of lied to you. Giving you these general reactions is basically like giving you the cliff notes for the novel, or the what's it called? Schmoop. Schmoop is apparently a new website I didn't know about until today, or like SparkNotes or something. The actual thing, this is not what happens. One of these doesn't mix with 2 of those and 2 of those to get that. There's actually a series of steps that go on. That is what a mechanism is. You will never, ever, ever be responsible for writing the full mechanism. I'm going to give it to you just like this. Now, notice we have one that says slow. What can you tell me about that step? It's going to be limiting. So what's it called? Anyone remember from pre-AP? It determines the rate, so it's called the rate determining step. Why does the slow step in the mechanism determine the rate? Determining. Because the other steps can't proceed without it. You're only as strong as your weakest link, right? So if we want to change the rate of this mechanism, we have to adjust the rate of the stuff in the slow step. Like increase the concentration of the stuff in the slow step, because doing it in the fast step won't help the reaction go faster at all. Okay? Attempted, yes. No, just don't worry about it. Semantics. You attempted. Yes, if you teach long enough, everything's just an attempt. All right, what I want to do is show you where the overall comes from. This is just like thermo, so this is going to be easy for you guys. To write the overall reaction, I'm going to cross out things that are the same on both sides. What can I get rid of? The HOI, okay. 2 OHs, right, on each side. So I end up with H2O2 plus 2I minus plus 2H pluses, making I2 plus 2 H2Os. Does that match above? Okay, so that's the overall reaction. Now, what are the intermediates and then what are the catalysts? An intermediate, by definition, is something that's produced in the reaction, in the mechanism, and then used up. In other words, we're gonna have crossed it out. Do we have any intermediates? OH minus, okay. And HOI, HOI. Do we have any catalysts? No, we really don't. But what a catalyst is? A catalyst speeds up a reaction, but that's not how we'd identify it. How do we identify it? As being present at the beginning and at the end. And this is also something we cross out. In other words, if I were to put a catalyst into this mechanism, I'd have it here and here. It would be there at the beginning and come out at the end, and it would be crossed out. Okay? All right, let's continue with this question. Notice, remember, this is a 3-step mechanism with the first step being the slow step. So sketch the energy profile for the 3-step mechanism and clearly label the rate determining step in your diagram. Before we do the one associated with this problem, I'm going to review what an energy diagram is, because you might see it again. That's what the coughing's all about. Do y'all remember this? Remember those? So we have energy on this axis. This is often termed the reaction coordinate, also known as just reaction progression. So what would this right here be called? Energy of the reactants. Good. Here, this would be energy of the products. At the very tippy top, I've got what? Is the top the activation energy? No. It's called the activated complex. Remember that? Sometimes they call it the transition state. So activated complex. It's the very, very high energy, unstable pseudo compound that's made right when reactants collide. And they're kind of doing their rearranging business. And then when they come back apart, we have our products. So this is the activated complex. So the activation energy, where does that come from? Well, that's the actual value from the reactant to the activated complex. So this is the energy of activation. That's the energy of activation. Can anyone tell me where we're going to find the heat of the reaction, the delta H? Products minus reactants. So this is our delta H. In this particular case, products minus reactants, is this endothermic or exothermic? This is endo specifically because we got products that have a higher energy than reactants. Where'd the energy come from? It went in. Exo would look like this. Okay? That's not very much higher, but oh well. Okay. So, how this translates to mechanisms is we need a hump for every reaction, because every reaction has its own activation energy. How many reactions do we have in our mechanism? 3. How can I translate to the fast-slow thing? What do I do? Tell me about the activation energy of the slow step. It's going to be the highest. The one with the highest hump is the one that's going to be the slowest. Think about running up the humps. Which one's going to take you the longest? Okay? So there was a 3-step mechanism, and the first step was the slow step. Is that right? So I don't know anything about exothermicity, endothermicity, so I don't have numbers. I'm just going to draw 3 humps, and I'm going to make sure the first one's the tallest. So that's tall, then I'm going to draw small, then I'm going to draw whatever. Okay. So again, this is energy. This is the progression of the reaction. Now on this picture, I'd like you to, progression. I'd like you to tell me where I might find the energy of the intermediates. The valleys. Yep, down here. That's an intermediate. That's an intermediate. Can anyone tell me where I might find energy of my catalysts? If you were to calculate it, yeah, but where would I just plot it on here? I'd have there and there. Okay? All right. Now is the important part. This is the reason we're doing this. We want to know rate law. What rate law would be expected if this mechanism were correct? So I'm going to go back. It's on the same page for you guys. I'm going to go back to the actual mechanism. Whenever I need to find the rate law, I go to the step that determines the rate, which is my slow step. Go to your slow step. How many molecules are slamming into each other in the slow step? 2. Since there's 2 molecules slamming into each other in the slow step, it is a second order reaction. First order with respect to H2O2, first order with respect to I-. Okay? So that's all order is. How many of those molecules are slamming into each other in the slow step of the mechanism? So to write out the rate law, it's simple. I can't find a K yet, a constant, because I've got no numerical values, and I'm aware of that. But what's one reactant in the rate law? I'm asking because I don't remember. H2O2. How many of them are there? 1. Slamming into what? I-, and how many of those are there? 1. So the terminology I'm expecting you to know is this is first order with respect to H2O, first order with respect to I-, and second order overall.
So if it was 2H2O,
It'd be second order with respect to H2O2. Now let me just show you a student mistake. A lot of students want to get their rate laws from an overall equation. They just want to go here and look. Do you see how, if we were to use this, how it would be messed up? First of all, there's no H plus in the slow step, so that's not affecting the rate at all. There's no I-, well, there's only 1 in the slow step. Here there would be 2, so your rate law would be totally jacked up. Okay? You can't use the reactants in an overall. You can only use the reactants in the slow step of the mechanism. Now let's talk about this H plus. This H plus is a reactant, so we kind of should put it into the rate law. So if I did want to include it though, any ideas? Because it's not actually colliding, because it's not in the slow. Exactly. And that's what 0 order is. 0 order means that the compound is in the overall equation, I should say overall reaction, but not where? Exactly, but not in the slow step. So it has no effect on the rate. So I can increase this concentration all day long and it would not change the rate of the reaction. Okay, and part D is just another practice. If we were to say that the second step were the slow step, that step, we take out our cross-outs when we're doing this. Go to the slow step. If this were the slow step, what would the rate law be? Just practicing. Rate is equal to K times HOI to the first times I minus to the first, which is not the case. This is just to practice writing this. Okay, let's go on to the next one. This is just the same thing we're practicing. What is the overall reaction? What cancels? I see 2 of those. I see 2 of those. Whoops, not that. I see 2 on this side as well. Does anything else cancel? No. So I have O2 plus 3 HBRs giving me 2 BR2s plus 2 waters. Where did I mess up? 4 HBRs is correct. I just missed it. 4 HBRs. Thank you. All right. Milo's laughing inside at me, deep down inside. He's asleep. Great. That's even better. Go kinetics. Woo. Do we have any intermediates here? HOBR? Huber. Huber. Do we have any catalysts? So Hober. Hober's a catalyst. Huber's an intermediate. October. Why is that funny? Just because it rhymes? It's not even October. It's not even the month of October.
2 months ago.
No, it was last month. Oh, it's December. You're right. My bad. Math is hard. All right. Sketch an energy profile. So we had a 4-step with what step was slow? The 3rd. So we have energy and we have our progression. I love my little straight line here. I want it to be a little bit nicer than that. It doesn't have to be perfect, but all right. So that was pretty good. What did I say the slow step was? 3rd out of 4. So whatever, kill it, whatever. And again, they all don't even have to end up when you're doing this. Like, they don't have to all end up in the same. We could do more like that. Yeah. All right. What would the rate law? So where do we go when we're looking at the rate law? Straight to slow step. So we're going to say rate is equal to K times HBR to the 1st times O2. Now, not everything is first order and first order. These are just first order and first order examples. Just look at how many are slamming into each other. That's all. And again, if you were to have done this from the overall equation, you would have gotten 4th order and first order, and that's wrong. So remember, you can only get this from the slow step of the mechanism. This is a prime example of an AP multiple choice question that was on this. Looking at this, the way I would do it is just quickly look at what the rate law would be of all the mechanisms, and your goal is to say, okay, which one of these mechanisms here of the 3 given are actually going to be the mechanism that produced that rate law. So I'm just going to write the mechanism for each one. A, it's a 1-step mechanism. It's not an overall. So this is being 1 step. It's the only step, so it is the slow step. What do we get for the rate law? NO2 to the 2. I've got a 3rd order overall there. Does that match? No, not so much. Okay. Looking at the next one, I'm going to go to the slow step, and I get rate is equal to K times NO2 to the 1st times F to the 1st. Okay? Does that match? Pretty close, but not quite.
Wait, do you need to put F2 to the 1st on your first rate that you did?
First rate. There is F2 right there.
Like F2, 1.
Well, 1 is understood. You don't have to put the 1s. Because it's a radical down here. That's a radical. That 1 electron. All right, and then this one, we have the slow step here. Rate is equal to K times NO2 to the 1. Does it match? Yep, so that's it. Okay? Yay. All right, last little problem. This is kind of fun. It's fun when you know what a rate law is and what a rate law looks like. When a certain substance's concentration is doubled, the initial rate of a reaction proceeds 8 times as fast. What is the order? There's some of you out there who just know immediately, who could tell me the answer right now. But if that scares you, write down a skeleton of a rate law. Rate is equal to K times A to an order. We don't know the order, okay? So look at what it's telling you. When a certain substance's concentration is doubled, the initial rate proceeds 8 times as fast. What is the order? 3. Math is hard. Third order, because 2 times 2 times 2 is 8. Does everyone see that? It's not bad once you know what that rate law looks like mathematically. Das ist alles. Frohes Wochenende. That means happy weekend. It's Friday.